lecture is Legendre differential equation. Here also it's the same. Okay, we do have some relations that we intend to remember, but we are going to start with something which is called the Rodrigues formula. Differential equation. So before we start with the first problem, let's just try understanding Legendre differential equations form. So the form is something like this. This is 1 minus x square. You can make a list of the forms for different differential equations. D square y dx square minus 2x dy dx plus n into n plus 1 y is equal to 0. So if you have any expression of this form, you are going to use the technique we use to solve Legendre differential equation. Okay, and the solution for such expressions might be something like y is equal to c p n x. Okay, so this p n x is nothing but the Legendre polynomial. So let's solve a problem. Okay, something which is called the Rodrigues formula. I'm going to look into that expression now. Okay, so the topic is Rodrigues formula. This comes under Legendre polynomial or Legendre differential equation. So solving it here. Rodrigue apostrophe s formula. Do Rodrigues formula. Okay, let's just see what's Rodrigues formula. The question that you might get is this: prove that p and x, so that's your polynomial that we are having. Okay, the Legendre polynomial also is called, is equal to, I've written p and x. Now the question is, what is p and x? Okay, so that is what I'm writing here. P and x is equal to 1 divided by 2 to the power n into factorial n. Okay, it's n, not x. D to the power n divided by dx to the power n, and this is x square minus 1 whole thing to the power n. So this is your Rodrigues formula, and what we're going to do now is we are going to prove it. Okay, and when we are going to prove this, we have to again know something which we have done in our lower classes. Where do we start? We obviously start from x square minus 1 to the power n, and then slowly we arrive at this result. Okay, let's do it. So let's just write down a note here before we proceed. Let me use a different color. Okay, and the note here is on Leibniz theorem. There is a theorem which you might have done in your graduation. In the basic maths course, it should be there. Okay, theorem. So what is Leibniz theorem? You might have a differential equation. Let's say a, b, you want to differentiate them, so you use the product rule, and that is only for one-time differentiation. If you want to differentiate it n times, you are going to use the Leibniz theorem, right? So d n u v. So let's say you want to differentiate a, b. This is only once. So what you do is you take a and then differentiate b. Then you take b and then differentiate a. A and b might be a function of x, so this d would be nothing but d dx, right? So this is what is the product rule is all about. Leibniz theorem also talks about a similar thing, but here we don't have one-time differentiation, we have got n-time differentiation. And you see this is d and dxn, so n times differentiation. So that means we should actually know Leibniz theorem, or we should revise Leibniz theorem. So Leibniz theorem is easy. The first thing is we are going to differentiate any of these variables n times. So let's say I'll differentiate u, and I will keep v as the not differentiated in the first step, right? The next step what I have is I have got n, which is the power here, and then I will have a constant here C1. We have different values of this constant which we are going to use directly because our aim is to not derive Leibniz theorem. I'm going to revise this only. Now this one would become n minus 1, so this one will reduce by 1, dn minus 1 into u, and this one now will be differentiated once, so it will be d of v. So idea is very simple, one increases, the other decreases in terms of differentiation, and then it will remain as n. This will be c2, n will depend on what is this. If it is n plus 1, this will become n plus 1. Okay, so this is 2, and then I'm going to take the next term, that means this differentiation will reduce by 1, so this would be d n minus 2 into u into d. This will increase by 1, so it is d square v, and this is going to keep on going. Finally we will have one last term where it's the other way around. We are going to take u outside, u won't be differentiated and v will be differentiated, so this will be d and v. That's it. So this is our Leibniz theorem. Okay, so I hope you remember this. Okay, I'm just doing it as a note, so let's just proceed. Okay, take a new page, use blue color, I think it's more visible. Okay, so let's prove this now. Prove Rodrigues formula. Proof. So proof, we have to start somewhere. So the starting point would be what will be our function. So let's say y is equal to x square minus 1 whole thing to the power n. This is our starting point. Okay, we want to differentiate it n times, but before we differentiate it once, we should not think about differentiating it n times. So let's say I want to find out what is dy dx. So it is n, x is x square minus 1 to the power n minus 1, and then we differentiate this and we will get 2x. So this is one time. Okay, and if we just multiply both sides with x square minus 1. Okay, so if we multiply both sides by x square minus 1, this will be dy dx is equal to n. Now this is x square minus 1, n minus 1 into x square minus 1, so that one power will go, so this would be x square minus 1 whole thing to the power n into 2x. Okay, so maybe you can just write it down, multiplying both sides by x square minus 1. Okay, please mention these things in your exam also, very important. Okay, उसके बाद क्या करेंगे, we are going to take up and going to simplify it a bit. X square minus 1, this is dy dx is equal to, now what is this x square minus 1 to the power n? This is nothing but y. This is nothing but y. So we are just going to write it down as 2 times n x y. You already have it here. Okay, so now we are going to take this. Now let's try to differentiate this. Okay, now let me just come this side now. So we are going to differentiate this expression x, okay, with respect to x. So differentiate with respect to x, how many times? N plus 1 times. You will easily know why it is n plus 1 times for getting the result. Okay, n plus 1 times. So that means I have to write it down as d of n plus 1. You also note it down, doing it slowly. X square minus 1 on this side, and this is dy dx. So dy dx, let me write it down as y dash. It will be more easy right now. Okay, is equal to d n plus 1. This is 2 times of n x y. Okay, we'll keep it this way, and we can also do something here. Put let's say I will put dy dx. It is only differentiated once as y, let's say y1, not y dash. Let me just put it as y1. Okay, let me just put it as y1. It'll be more easy. You will see that it is more convenient, because then, if you're differentiating it n times, you can just simply write it down as y to the base n. Okay, just a notation to escape the confusion again and again. Okay, so now let's see what we can do here. We are going to use the Leibniz theorem, and this is one function, this is one function, and this is another function. So these are the two functions that we have. So as per Leibniz theorem, first we have to uh, take the differentiation of the first function. Okay, let's say this is y1, and then keep the other function constant. We are not going to do anything with it. X square minus 1, right? This is the first function, plus, okay, I think I should have written the Leibniz theorem in this page. Then we have got nc1. What is n? N is whatever times the differentiation is taking place. This is n. So here we are differentiating it n plus 1 times. So that means in place of n, this would be n plus 1. C1 will remain. I'll take one more. Okay, one more differentiation. So that means I will just write down one more here, plus this will remain as n plus 1 into C2 now, remains the same. Okay, or maybe I can take it in the next line, otherwise it becomes a bit confusing here. Okay, so this next term would be nothing but plus, okay, and this is n plus 1 C2 d. This is now reduced by 1 again, so this is dn minus 1 y1 into d square to x minus 1. Okay, and that's it. We don't proceed further. Okay, the reason is, if I take d3, okay, this is x square. If I take d3, I'm going to get a 0 here, because d square means ddx of x square minus 1 and then ddx of that. Okay, so if I write it down in this way, okay, just to be clear about Leibniz theorem, why it is good and why we're going to get it. So if I just write down something like this as d of x square minus 1, that means ddx of x square minus 1, I'm going to get it at 2x, right? And if I take d square of x square minus 1, this will be ddx of 2x, because one time differentiation is already done. So this is x, only 2, sorry, not x, only 2. Now if I take d cubed of x square minus 1, this is going to be ddx of 2, so which is going to be 0. So that means there is no point taking the third d. This just can be complete at this particular point. So this is on the left hand side. Let's do it for the right hand side. Okay, so for the right hand side, equal to is the right hand side, so 2n is a constant. I can take it out, I don't need it anyway, and then I can do the Leibniz theorem for the other terms. So what I can do here is, the first thing would be dn plus 1, let's take for y, into, I will keep x as it is, and then I will take the n plus 1 into c, and then c1, let's write it down, and this will reduce by 1, so this is dny, okay, into, this will increase by 1, so this will be dx. There is no point taking it after this, because ddx of x is 1, and then you take one more order, it will become 0, so you don't need it. So this is our entire expression. Okay, we are going to just build everything from here itself. Okay, so let's just use some notation so that things becomes a bit easy now. So this is already differentiated one time. You are differentiating it n plus 1 times more, so that means this is differentiated n plus 2 times. So what I can do is, I can write down this x square minus 1, this term, and this can be written as y of n plus 2. This is just for ease, okay, and I think it's not confusing also. N plus 2 times differentiation, n plus 1 times already done, you're doing it 1 times more. Okay, so that is okay, plus this is n plus 1 The value of c1, if you look, this will be 1. Okay, c1 would always be 1. So this is n plus 1, okay, into y dn y1, okay, dn y1. So that means this can be written as y n plus 1. Don't get confused here, please take a look very carefully. Into, this is d of x square minus 1, so this is nothing but 2x. That's done. Then I will take plus, let's write this n plus 1 c2. Now c2 is n by 2, okay. These constants are there which you need to remember. So this n plus 1 into c2 will become, n plus 1 will be there, and c2 would be n by 2. Is there in the theorem, but we are not deriving it anyway. Anyway, don't need to remember so many things here. Only for this expression we are going to use the Leibniz theorem. We may not be using it for too long, so we don't need to know, remember c3, c4, c5 and so on, okay. Not too much to remember here. So it is n into n plus 1 divided by 2 into let's not miss the term here, this is n minus 1 and this is y1. So that means n minus 1 and then 1, it will get reduced, so it will be yn. So I can just simply write it down as yn. Same logic, yn into 2, y2, because ddx of x square minus 1 was 2x, and then ddx of x square 2x is 2, so that's that 2. Okay, so that 2 we have, equal to, let's write it down on this side, this would be 2n, then this is, there is no such, it's only y, so I'll just simply write it down as y n plus 1, okay, into x, first term. The second term I will have 2n there again, I will have n plus 1, c1 is 1, so I don't need to put it there, and then we have got dn of yn, so I'll again write it down as yn, and then dx of x is just 1, so I don't need to write it down, right? So काफी है. So this is my left hand side and right hand side, okay. Now let's see what we can do. Now we are going to keep modifying things here, okay. Let me just take it to the next slide. Pages. Okay, so we have got the left hand side and the right hand side. Now let's just see what more modifications we can do and changes, okay. Let's see, it's going to be a very long derivation, okay. Even I lost track sometimes, so I'm going to do it slow. So then what we are going to do is we are going to combine the terms here, going to do basic algebra. X square minus 1, we have it, and then we can actually write it down as y of n plus 2, okay, plus, now let's just combine this yn plus 1 terms, everything together, okay. Yn plus 2, there is only one term, yn plus 2, there is only one term, okay. Just a second. Okay, so yn plus 2, okay, and then we are going to write down all the yn plus 1 terms together. So what we'll do is this, just open this bracket up, okay. This is 2x into n, so I'll write it down as 2 times of nx, then plus of 2x, this side it's done. What we have it else, yeah, yn plus 1 is here, so this is 2nx, so I'll just write down on the other side, so this will be minus of 2nx, okay, and we can close the bracket. This is yn plus 1, okay, done. And then we can actually combine the n terms, yn terms, okay, and here we have got n square, this one, this 2 and this 2 will get cancelled, so we've got n square plus n, okay, and on the other side we have got 2n square, so it is minus of 2n square, and then this is again minus of 2n, okay, into yn is equal to 0. So you can see we have combined all the terms here. Let's just do some modifications here. 2nx will get cancelled, n square minus 2n square and everything can be joined here, okay. So let's just do it. So I'll write it down as x square minus 1 And dn plus 2, dn plus 2 can be written as d square yn means we are differentiating it n times, so it is the same thing, dx square. It can be written in this way, plus this is just 2x which remains here. Okay, so that means we can just write it down as 2x uh, yn plus, so similarly I can write it down as dyn dx, same thing, plus, so n square minus 2n square is minus n square, n minus 2n is minus n, so I will just take out that minus sign. So I'll just take out this minus sign. Okay, so I'll write it down as minus n into n plus 1. Okay, and this is yn is equal to 0. Just look into this modification. If you look here, this is minus of n square minus of n. We can take out minus n common, so this would be nothing but n plus 1. Okay, and that's why I've written it this way, so it's easy. Okay, once done this, let's just check what else we can do. We can actually get rid of this minus and write it down in the Leibniz form. So if I take minus common everywhere, this will become 1 minus x square into t square yn divided by dx square minus 2x dyn dx plus n into n plus 1 into y to the power n is equal to 0. Okay, let's just have a look at this. Okay, let me just go back to the previous section. Yeah, check this. Okay, this is there, minus of 2x dy dx plus n into n plus 1 into y is equal to 0. So that means this is actually a Legendre differential equation if we actually differentiate it and use the Leibniz theorem. So we are getting it a Legendre differential equation, and the solution to such equation is this. So we are going to use this solution and find out the form. Okay, that's the aim. That is what we are doing till now, so we should not lose that track. So it is yn, and that's why I've written it in d square yn. You might say that I should written it, can also write it down as d and y square y2. We can write it, but that way we are not going to get this form, and then we don't know what is the solution. The solution to this is this. So that means we have written it in the form of Legendre's differential equation. Okay, and now we know what is the solution. Okay, and just to make things a bit simpler, we can just say that let yn is equal to z, because that expression says about only one variable. So I have to write it down in the Legendre's differential equation form exactly. 1 minus x square, this is dz divided by dx square minus 2 times of x dz divided by dx plus n into n plus 1 into z is equal to 0. So if we have this expression, okay, we know what is the solution. Okay, and the solution is, to this equation is nothing but z is equal to c p n x. This is the solution. And what is my z? Z is yn is equal to c p n x. Now what's my aim? My aim is to find out what is c. I don't know what is this constant, so let's just try to find out what is my c. Okay, so let's go to the next page. So we have written the solution as yn is equal to c p n x, and what is my yn? Yn is nothing but dny. Don't get confused here. dxn, remember what the notations we are using, is equal to c p n x. Okay, let's mark this as expression 1, and we can actually find out these values at different values of x. So let's say d n y dxn at, let's say, x is equal to 1. At x is equal to 1, this would be nothing but c p n1. Now although we have not done it, but please remember that when we take p n at 1, the answer you are going to get it as 1. Okay, let's see if we can derive it, but this is a result for the polynomial. We are going to check it that it becomes actually 1. Okay, I'm going to say that later, but Pn at 1 is equal to 1. So that means this is 1. So that means we can write it down as dny dxn at x is equal to 1 is equal to c. So we know what is c. Okay, now our aim is to find out what is this dny dxn. If we differentiate it n times, what is the value? If we know it, we can know what is the exact form of c that we have. Okay, so we are going to do it now. So the same thing. Okay, it's the same thing. So now you have to again look into it very carefully. It's going to be a bit confusing. Okay, when I was practicing, I also got a bit confused here. Okay, so let's just take this look. So now I have to find out what is dny dxn. For that I have to start with y again. So let's just do it. Now y is equal to x square minus 1 whole thing to the power n. Okay, this implies obviously that y can be written as x plus 1 to the power n and x minus 1 to the power n. I hope you understand this. I'm separating it out. I'm getting two functions now, and now I can use the Leibniz theorem. Okay, so maybe I can write down this differentiating with respect to x and using Leibniz theorem. Okay, we are going to check what happens here. Okay, so that means that I'm going to do it d and y. This is d and y, right? So this is equal to dn of x plus 1 to the power n and then x minus 1 to the power n. Okay, so let's use Leibniz theorem. Okay, so that means dn means it is simply dny dxn. No confusion with notation. I'm telling you again and again, very important. This should be dn, and then I will take, let's say, x minus 1 to the power n, and then x plus 1 to the power n will remain constant, nothing changes here, plus I can take n, it's n time differentiation, so it is nc1, and then I will reduce this by 1, so this will be n minus 1 of x minus 1 to the power n into, I will increase this by 1, so I'll differentiate it x plus 1 to the power n. Okay, and so on. So I will just write down one more term here. This will be nc2, this will be d reduced by 1, n minus 2, x minus 1 to the power n, this is increased by 1, this is d square, x plus 1 to the power n, and then plus this is x minus 1 to the power n, final term, x minus 1 to the power n into d of x plus 1 to the power, dn of x plus 1 to the power n. Okay, so this is there. Okay, once we have written this, let me just show you something here. Okay, I think it's very important here. Just a sec. Did I miss anything here? Yeah, maybe. Okay. So I'll give you a note first before we actually proceed. Again, this is not important that you include for your exam, but it is important that you understand this note. Okay, the note is this. Let's write down d square of, let's say, x minus 1 square. So if I do it, we have already seen how to do it. Okay, we can, I have to differentiate this, so maybe I can take this as 2 of x minus 1. So ddx of x square, x minus 1 whole square will be 2 times of x minus 1, and then again I take the d of that, so this should be nothing but 2. So that means this is 2 factorial. Similarly, if you take d cubed and let's say this is x minus 1 cubed, you are going to get something like this. This is d square, and this is 3 times x minus 1, which is, again, you take the d square, d of that, so this will be d, and this will be nothing but this is x minus 1 square, right? And this will be 6 times of x minus 1, and then again you take the d of that, you're going to get 6, which is nothing but 3 factorial. So whatever is the differentiation, and if the power of this variable is also the same, you're going to get the factorial. So that means if I take a term something like this, dn x minus 1 to the power n, the answer is going to be n factorial. This is very important, okay? Why? Because we are going to use it here. See, dn x minus 1 n. I'm straight away going to write down n factorial here, and you'll ask me why? How did I write it down? Okay, and that's the reason that I'm doing it here. That's the note here. D square x minus 1 whole square, you do it, you'll get 2 factorial. Cubed, you do it, 3 factorial, and so on. So this is going to continue, okay? So that's the reason that for this particular term, I can simply write it down as factorial n. Okay, so let's just do it now. So let me just write down this now. Okay, so that means therefore we can have dny dxn is equal to let me just rewind and check. See, this is factorial n x plus 1 n. So the first term would be factorial n x plus 1 whole thing to the power n, okay, plus, and check here, you have got an x minus 1 term here, okay, and this is also having an x minus 1 term, okay, this is also having an x minus 1 term. All the terms are basically going to have your x minus 1 term, okay, that will always be there, okay. I'll tell you the reason for this, okay, because maybe one more note is important here. Okay, one more note I will give it to the next page. This note is on this. Now let's say this is d square and not d cube. This is d square and this is x minus 1 cubed. Now let's differentiate this. What are you going to get? First time you're going to get d, and this would be 3 times of x minus 1 square, and then you do it, you're going to get 6 times of x minus 1. This is the final answer. So that means you're going to get an x minus 1 term here. So this is 2, which is 1 less than the power. So that means d n x minus 1 n. Now if this is 1 less, that means minus 1. Whatever term you are going to get, okay, is going to be some constant, some value like 6 into x minus 1. Please remember this, understand this, x minus 1. Now let's just get back here. This is dn minus 1 x minus 1 to the power n. This is dn minus 1 where dn minus 1 n minus 2 x minus 1 to the power n. So all these terms is going to have an x minus 1 term with them for sure, because this is 1 less than this. So that means all the other terms which are there will be having an x minus 1 common. I can take it out within bracket. I can write down all terms, not repeating everything, just writing down all terms here just to keep it simple. Done. Now you see you are going to have this result, okay, x minus 1 is equal to 0 at x is equal to 1, okay. So therefore dny dxn at x is equal to 1. Now you'll ask me why x is equal to 1, because we found out the constant c at x is equal to 1. So that means at x is equal to 1 we can just replace it. This is factorial 1, factorial n, because it's only for x. This will be 1 plus 1, so this is 2 to the power n plus 0. So that means this is 2 to the power n into factorial n. That's there. So there means c is equal to this, which is equal to 2 to the power n factorial n. Done. I got c. I got the constant here. Very important step. So markings for such questions will be stepwise, okay. So that's very important that you write it down clearly. So therefore I told you the solution here, d square y, sorry, not d square, dn divided by, let me just write it down clearly, last step, dny dxn is equal to factorial n c, that means 2 to the power n into pn x. Okay, and that means I can write down the form of pnx. Pnx is equal to 1 divided by factorial n into 2 to the power n into dny dxn. So that means this can be written as dn dxn, and my y is x square minus 1, okay, whole thing to the power n. So you see, after such a long derivation, we are going to get the Rodrigues formula. That's your Rodrigues formula. Derivation, descriptive question, definitely 8 marks. If offline, if online, it's 5 marks. Okay, so you have to remember this. Okay, let me just revise the steps quickly for you. We are talking about Legendre differential equation, and the Legendre differential equation should be of this form, and the solution for such equation is c into pnx, where the pnx is the Legendre polynomial. Now there is a formula which is called the Rodrigues formula, and here you have to prove that the Legendre polynomial that we are talking about is equal to 1 divided by 2 to the power n factorial n ddx of n times x square minus 1 to the power n, right? So we have to do it. For that we need to know few things. First thing, Leibniz theorem. If we differentiate a set of two variables n times, we have to use this formula, where the differential of one increases by 1, the other decreases by 1, and there are constants involved like nc1 and c2. c1 is 1, c2 is n by 2, and so on. Okay, so we're going to use that result. Next, we have to start somewhere, and if you just look into this, that means we can start using this function. So we're going to take up x square minus 1 whole thing to the power n. We are going to differentiate it just once, okay, and then we are going to modify it and write it down in this way. The aim is actually to write down this and get it in the form of a differential equation, which will actually represent the Legendre differential equation, so that we can say that yes, the solution for this would be c pnx. Okay, so let's just write this down. We have written this, we modified this accordingly. We see there is a two function case here, there is also a two function. We can use Leibniz theorem, expand it, okay, and simplify it. So when we simplify everything, we are going to get it in the form of a Legendre differential equation. Okay, and the solution for that Legendre differential equation is something which you already know, is this. Okay, is this. So now the aim is to find out what is my constant. So for finding out the constant, what we do is we are going to take x is equal to 1. We see that this is equal to c. Okay, this is equal to c. Now we don't know what is this, so that means we have to differentiate this y n times. So let's just differentiate it, separate this out, and then we are going to use the Leibniz theorem again. But then we are going to use something which is logical, but sometimes we miss if we don't understand it, and that's why I've given you these steps, that if we differentiate it the number of times same as the power of the variable, we are going to get the 2 times the factorial of that power. Here also factorial of that power. So based on this, we can write down this as factorial n. But what about this? This is n minus 1 and this is to the power n. So if it is reduced by 1, this will come once at the front, that's for sure. If it is reduced by 2, this will be x minus 1, x minus 2, and then it will be there. We can keep on doing it, but we are not going to do it because we are going to find it out at x is equal to 1, and we know if we get one term x is equal to x minus 1 outside, everything will be inside. If I put x is equal to 1, this entire term will become 0. Makes it easy. This will become 0. I've got the constant as 2 to the power n factorial n. We put the values here, we find out what is the value of Pn, and this is our Rodrigues formula. So this is a very important result in Legendre polynomial. You have to practice it. I won't suggest you, to just leave it like this. If you just have a look into it, probably you're going to make a lot of mistakes. I don't suggest you to even remember anything. Leibniz theorem is something which you have done in your lower class, so obviously you have to remember. You cannot derive everything in this class. Also the value of the constants and C1 and C2, that you need to know, because we also cannot derive that out of scope.